Before we get started, let's talk about what Blueshift does. This slide here is a very high-level summary of Blueshift. A single-line description. We are an AI-driven customer engagement platform. Blueshift brings together an integrated CDP, cross-channel marketing hub, and AI to help you deliver personalized experiences at every stage of customer journey. This is more of a non-technical description of Blueshift. Let's dive a little deeper into what Blueshift does from a little more technical standpoint. Blueshift, data plus AI plus orchestration, all in one platform. This picture here shows Blueshift as a continuously running machine powered by AI decisioning, real-time customer data, cross-channel delivery, helping drive the one-on-one customer engagement. Let me simplify this a bit. Let's think of Blueshift as a black box. What's the input? It's user data, activity data, CRM data, web and app behavior, data from data warehouses. All this data is fed into Blueshift. Blueshift processes this data and intelligently generates some output. What's the output? Email messages, paid media targeting signals, push messages, website, user data augmentation, derived attributes, scores, etc. Now, you can think of Blueshift as a continuously running machine which gets some input, processes it, generates some output. And that output helps drive customer engagement, which generates more data, which again serves as an input to Blueshift, helping drive more meaningful engagement. So in one of the talks earlier, Arvind mentioned about like data flywheel. So you can think of Blueshift as a data flywheel. Let's talk about the backend tech stack. What powers all this? We talked about what Blueshift does, but doing that at a scale where you are ingesting billions of events and processing data for hundreds of customers, it requires a very complex and robust backend. Our current tech stack consists of more than 250 microservices, close to 50 different database clusters, a very write-heavy backend, thousands of data streams, billions of data points processed daily, more than 50 terabytes of data processed on a daily basis. We have real-time as well as batch processing. Before we deep dive into our current architecture, I want to talk about our legacy architecture and the challenges we used to face with that. The picture here shows a very high-level overview of our legacy architecture. We have a top layer which consists of API, dashboard, and any inbound data integrations like data warehouse connectors, etc. Then we have an intermediate compute cum backend layer which handles all the data processing, plus acts as a compute engine. For this talk, I have shown very simple relations between the services. The actual relations are more complex, and we have a lot more services than what's shown here. At the very bottom is our storage layer, which consists of different databases and other data storage destinations like S3, Elasticsearch, MySQL, ScyllaDB, data warehouse connectors. Now, what were our major challenges with this? First and foremost, we had very hard inter-service dependencies. Solid lines here between multiple microservices represent hard dependencies. The backend system was very tightly coupled. We had weak fault tolerance capabilities. There was no customer or service level SLAs that we had. Slow recovery from outages, multiple systems for pub sub, queuing, data streaming. We had Kafka for data streaming, NSQ for pub sub, and Sidekick for queuing. Data loss during outages, that was one of our biggest challenges. Higher cost managing these multiple clusters, having different systems for different purposes, and the list goes on. Let me walk through an example showing one of the major challenges with this architecture for us. This is our stack when everything is running smoothly. Let's assume that our search service starts seeing slowness. Due to hard inter-service dependencies, the slowness in search service starts propagating to reporting service. Now, the slowness in reporting service will propagate to the user management service. Slowness in user management service causes slowness in campaigns. That causes slowness in event processing and catalog. And eventually, all these cascading failures bring down the whole backend. That will eventually start causing errors in dashboard and API, which are sort of customer-facing services. And with that, boom, we have a full outage. So what was missing in this architecture for us? One word, resilience. Resilience, what does it mean? By definition, resilience is the intrinsic ability of a system to adjust its functioning prior to, during, or following changes and disturbances so that it can sustain required operations under both expected and unexpected conditions. For example, hardware failure on some EC2 machine shouldn't bring down your whole platform. Some unexpected increase in traffic from a certain customer shouldn't cause issues for other customers. Disturbances could be in multiple forms. Resilience is about being able to function rather than being impervious to failure. What constitutes a resilient system? It's not the one with absence of something. Hardware failures, network failures, operational mistakes, these are all inevitable. Resilient system is the one with presence of something. What's that something? It's about the presence of ability to recognize, adapt to, and absorb changes and disruptions, some of which might fall outside of what the system is designed or trained to handle. A service should auto-scale if there is no more traffic. A failure in an EC2 machine should automatically trigger actions that switch traffic to some other replica. There could be a lot more examples to showcase resilience. Now, with resilience being the core focus, we decided to rebuild our platform with new architecture. When we started reimagining our architecture, we decided to list down what our requirements are from the new architecture. The requirements we came up with were a fully event-driven architecture, asynchronous updates for majority of the data, very important next to requirements, customer-level SLAs, and service-level SLAs. This is very, very important. I will talk more about these. Data streams fan-out. I will discuss this also in detail later in the presentation. Seamless auto-scaling for peak traffic. This is very important for us because we need to run efficiently all the time, and at the same time, we must maintain our SLAs even under peak load. Isolation of data into different tiers. All the external data, as well as the internal events that we generate, consist of wide variety of actions, each with different SLAs. For example, user updates, transactions, etc. need to be processed with minimum delay. However, events like email sent actions, file uploads, bulk data loads, AI-generated scores can be processed with some delay. Next was higher degree of fault tolerance. Hardware failures, network glitches, service outages are inevitable. We wanted a system which can keep operating within some acceptable degradation, even when we suffer certain failures. Last but not the least was infrastructure consolidation. We didn't want to have multiple systems for pub/sub, streaming, queuing, because it increases the operational complexity. You need more training, you need more people to manage multiple systems, and that kind of becomes an issue. We earlier discussed an example to show how our whole platform used to go down just because of a single service outage. You all guys saw that, right? Let's take the same scenario and see how our new architecture handles the same situation. This is our stack when everything is running smoothly. Let's imagine that the event processing service starts experiencing slowness. It could be because of some hardware issue. There could be a bunch of other reasons. As the service is experiencing slowness, what we will start observing is that backlog starts building up in some Pulsar topics. Until the service keeps having issues, backlog will keep building up. Service is still down. Someone is still working on it, trying to get it back to normal working conditions. While that's going on, backlog keeps going up. While all this is happening, what's the impact on the platform? What should we go and update on our status page? It's just that event processing is having delays. We are slower in processing all the incoming events in our platform. It's not that whole platform is down. Campaigns, user management, all the other services are operating normally. Now, we see service is still down. Backlog has grown significantly. OK, someone resolved the service has now recovered, backlog starts coming down. At this time, someone will, there are auto-scaling rules which will ensure that service is running at its peak capacity to drain the backlog faster. Backlog is reducing. Backlog is back to normal levels. System is fully functional now. As we see in our new architecture, we are able to handle small service outages gracefully without letting it impact the whole stack. I will now talk about how Apache Pulsar fits in our new architecture, helping us achieve some of our core objectives. First and foremost, a truly multi-tenant system. I don't think I need to explain further on this. I'm pretty sure most of you are fully aware of this. Offers separate compute and storage layer. This is very important for us because we have different types of data streams, each with different requirements. Some streams are very storage intensive, like we don't have a high throughput requirement on those streams, but we need longer retention on those streams. And some streams are compute intensive. We have very high throughput requirements on those streams, but we don't need any retention at all on those streams. Never need to worry about message loss. Most of you will be aware of Pulsar's very durable storage architecture. There have been some very good articles published by Stream Native on this. I would recommend all of you to go and read them. They're really good. Consumer fan-out. Majority of our data streams need to be consumed by multiple services. We didn't want to create copy pipelines with duplicate data flowing in those. Single cluster for pub/sub queuing and streams. That was very important for us from cost-saving perspective as well as operational simplicity. Dispatch rate limits. This is a very handy feature to enforce customer-level rate limits within streaming system itself without having any rate-limiting complexity built into the consumer. This has been very handy for us. We had streams where we had put some rate limits to ensure that it doesn't overwhelm the systems, downstream systems. Message replay. This is also very useful at times. If a downstream system has transient issues, you can go and replay the data streams via Pulsar rather than involving the consumer. Obviously, there are certain considerations. Operation has to be idempotent. I think we also saw in the fireside chat that we talked about how it could be very useful for agentic systems, where if things go wrong, they can go and replay the messages again. Message TTL. This is also very useful if you have a data stream containing data which is relevant for a very short period of time. So you don't want to process some event where it's already sort of too late to process it. It's not relevant anymore. So you can use message TTL in those cases. Last but not the least, topic organization. This picture here shows how we have organized data into different tenants. We have tenants for catalog, campaigns, event processing, user management, data archival. Over here, I will take a pause. I will tell you one interesting thing. When we decided to adopt Pulsar, it was in the very early days. I will tell you guys a joke. Most of our engineering team is back in India. So in the early days, when they used to Google Apache Pulsar, the results that they used to get is motorcycle ads. And I will tell you the reason for that. If anyone is from India, they will understand. In India, there are two popular motorcycles. One is TVS Apache. Another is named Bajaj Pulsar. So Pulsar was not ranked high enough in the search engine algorithms that it would start like showing Apache Pulsar. So I just want to give this example to show how early we were in adopting Apache Pulsar in our system. OK, let's zoom in and see how topics are further organized inside each tenant. Let's consider the user management tenant. The tenant consists of namespaces for user updates, file uploads, events, data science scores, jobs. Each namespace has its SLA set via namespace policy. For example, we have different retention requirements for user uploads versus jobs versus events. We also have different rate limiting requirements for each. There are a bunch of settings we enforce via namespace policy. It makes things really easy for us. We have different topics for different customers. So for example, over here, you can see under user updates namespace, we have topic for customer 1, customer 2, customer 3, customer 4, and the list can go on. This helps us provide isolation between different customers and avoid noisy neighbor problem. Now, that's really important. Earlier, I mentioned about like having customer level SLAs. This is something which helps us achieve those customer level SLAs. For some internal data updates, we have topics for different use cases depending on the SLA and the volumes. For example, for data science generated scores, we have different topics to process daily scores, weekly scores, and monthly scores, because each one of those have different SLAs. So that's why we have separate topics for each one of them. Most of the namespaces that we have within our system have topic auto creation enabled. This makes things very easy. Whenever a new customer is onboarded, you don't have to go into tens of hundreds of namespaces and configure topics for them. You just do minimal configuration, and as soon as the customer is created, as soon as the data starts flowing in, topics will get auto-created. And that's very handy for us. It's very useful. All right. I will now discuss a couple of production examples to showcase how we have leveraged certain features of Pulsar and our asynchronous indexing pipeline to perform index operations without incurring any downtime at all. So our search and segmentation backend is powered by Elasticsearch. We have hundreds of indices spread across multiple clusters. We ingest billions of documents, including user updates, events, etc., into Elasticsearch daily. From time to time, we have to do operation on these indices without incurring any downtime. The operations include index relocation from one cluster to another, increasing number of shards on an index, force merge operation. Let's see how we achieve these operations so easily in our new architecture. The first example we'll discuss is index relocation. This is the high-level design of our indexing pipeline. We have a custom plugin that we have built and installed in our Elasticsearch clusters, which consumes data from Pulsar and indexes it into Elasticsearch indices. Now, this is more of a pull model rather than a push model for indexing data into Elasticsearch. And I will show you some of the benefits with this model, where like if a cluster is slow, it doesn't impact the data like indexing for the other clusters. So it completely decouples that like data processing and the sort of storage layer. The indexing we have a topic for each account in Pulsar. The indexing plugin inside Elasticsearch uses a shared subscription on Pulsar to consume the data. Now, I want all of you to pay attention over here to see how we have named the subscriptions. The subscription name convention is cluster name.index name. Let's consider we have to move index C for account 3 from cluster A to cluster B. Traditionally, doing this operation would require a complex reindexing process if you want to not have any downtime at all. And the process is, like reindexing process is very time consuming and very error prone. In our new architecture, we are able to do this operation within a very short time and without having any downtime at all. Let's see how we do it. The first thing we do is we create a subscription for the new index on cluster B. I earlier mentioned what our naming convention is. Now, since we are going to relocate index C from cluster A to cluster B, we create a subscription first, which is cluster B.index C. And yeah, that's our first step. As you can see over here, the next step we do is create a snapshot of index C in S3. While the snapshot is in progress, we can see that the second subscription that we created on Pulsar has started accumulating backlog. Snapshot is still in progress. Backlog on the new subscription is rising. Snapshot is complete. Backlog is still growing. Next step is to restore the snapshot on cluster B, because that's the cluster where we are going to relocate the index. While the snapshot is in progress, while the restore is in progress, we have backlog still accumulating on the new subscription. So it has grown significantly. But at this point, there's no impact on any production traffic, because the search is still served from index C on cluster A, and the data getting ingested into that index is having no backlog. Restore is complete. Good. OK, new index now is up and running. It's healthy. So the plugin detects that, OK, the index is healthy. It connects to its subscription and starts consuming the data from Pulsar. Backlog will start coming down. Further down. Backlog has drained. Now, at this point, we have two consistent indices having, theoretically should have the same data in both of them. But we need to verify that. So what we do is we run verifications to ensure two indices are consistent with each other. So as I mentioned, while all this process was going on, search traffic was still served from cluster A for this index. If the verifications pass, we switch the search traffic to index C on cluster B. Once that is done, we can safely delete the index on cluster A, and we have successfully relocated the index from one cluster to another without even a single second of downtime, leveraging Pulsar and our asynchronous indexing pipeline. The next example we'll discuss is force merge or increasing shards. Anyone not familiar with Elasticsearch? Force merge is used for on-demand merging of segments. And Elasticsearch does it automatically as well, but sometimes if you have a lot of deletes happening on Elasticsearch indices, sometimes there's a need of force merge operation. Also, if you want to increase number of shards on an index, Elasticsearch has an API called split, which can increase the number of shards on an index. Both these operations in Elasticsearch are very resource intensive. If you run them on a live index, which is serving search traffic and also ingesting data, you will for sure run into experience degradation, which in some cases may be very significant. Let's see how we do these operations without any downtime or any impact on performance. Let's consider we have to run split or force merge on index C, which is hosted on cluster A. For this example, this index is currently the version 1 of the index. For clarity, the naming convention I used here has a version suffix in the end. So in the picture here, you can see an Elasticsearch cluster named Shadow Cluster. This cluster doesn't serve any search traffic or any production traffic. And we use this cluster only for these operations, running force merge, split, any of these resource-intensive operations. So OK, similar to our index relocation, the first step we do is create a subscription for the new index version, which is index C_2. As you can see, we have created a subscription named index cluster A.index C_2 in the Pulsar topic. We take a snapshot of index C_1 to S3. As snapshot is ongoing, backlog on the new subscription will start rising. We restore the snapshot on the shadow cluster. Once restored, we start split or force merge operation using the Elasticsearch APIs on the index inside shadow cluster. Even if it takes full resources, there is no issue as the cluster is not serving any search traffic. We have seen at times that our shadow cluster keeps running at 100% CPU, but it's not a problem for us because that's what it's meant for. So we are able to get 100% from the resources that we have. Operation is complete. Backlog has increased on the new subscription. Next thing we do is restore the index from shadow cluster. Now, this is very important. Now, we ran the force merge and split operation on that index inside shadow cluster. We take another snapshot of that index into S3, and via that snapshot, we restore this index, which has been now optimized, like splitted into more shards, onto the original cluster, but we use a different version suffix. So in this case, the original index was index C underscore 1. Now we restore it with index C underscore 2. Once fully restored, new index is up and running, it's healthy, and it connects to its subscription and starts consuming data. Backlog starts coming down, further down, all the backlog has drained. Again, like our index relocation process, here we have two consistent indices having same data and ingesting data in parallel without having any copy pipelines. They are ingesting data from the same topic. We run verifications to ensure that both these indices are consistent, there's no mismatch, everything is good. If verification is successful, we go and switch the search traffic from version 1 of the index to version 2. So now the search traffic will be served from index C underscore 2. After this, the old version of index is deleted. As you saw, we completed a very resource-intensive operation of the index without impacting production traffic or having any downtime at all. I will tell you one interesting thing how it's possible with Pulsar. Pulsar has a different concept of retention versus backlog. So we don't need to worry about retention while this operation is going on, even if it runs for multiple days. As long as we have enough storage there in our bookies, we can accommodate that backlog. We definitely need to have enough backlog quota on the Pulsar topic to ensure that we don't start having back pressure on the producers. All right, key takeaways. The first one is that infrastructure consolidation drives cost and complexity reduction. We replaced Kafka, NSQ, and Sidekick with a single Pulsar cluster, eliminating the operational overhead of managing multiple messaging systems. And one unified system for pub/sub, queuing, and streaming reduces training needs, operational complexity, and infrastructure costs. Event-driven architecture enables true fault isolation. I think we discussed the examples how good it makes your overall stack in terms of resiliency. Customer-level SLAs become technically feasible. Now, I showed you like how we did the topic organization in our Pulsar to ensure that there's no noisy neighbor problem. We are able to give SLAs to each customer. Imagine a situation like, if you have a shared topic and one customer uploaded a couple of events or a couple of users, and suddenly he's seeing that they are not getting processed. Can you go and tell the customer that, hey, the reason it's slow is because we had one other customer who uploaded a million records and it caused backlog in our pipelines? No, right? So having different topics for different customers ensures that you are able to give a minimum SLA to each one of your customers. Recovery capabilities. We just saw how easily we can achieve zero downtime index operations. And even using the Pulsar's like message replay capabilities, at certain points, if we have issues in our downstream databases where something went wrong, we can easily go and replay messages right from the Pulsar, and we don't have to involve the consumer at all in that.